Welcome to Xiaolu.x, where code creativity and conversation collide. Today we open a new chapter, the autonomous coding revolution. This visual is your guide through the shift from general language models to specialized code LLMs that generate
General AI models are dangerous for coding. They change one line, but break hidden dependencies 200 files away. One quick edit from an AI assistant can set off a chain reaction you never see until your build melts down.
Static analyzers, they map the whole graph. General models, they don't even know it exists. That's why one fix can...
Old AI wrote code like a lone programmer. The new generation, it acts like a whole software company inside a chip. A CEO plans, a CTO architects, developers build, testers check, each role simulated and working in parallel. Compared to the old single model approach, it delivers apps in seconds with quality baked in.
Here are 5 key impacts of the AI coding boom. 1. Models now hit 95% success on benchmarks like HumanEval. 2. Commercial tools such as Copilot and Cursor have taken over the market. 3. We're moving from passive helpers to active agentic teammates. And 5.
Welcome to the deep dive. Today we are cutting right through the noise to give you the essential architecture of the future, delivered straight from the source. For this deep dive, we're immersing ourselves in the LLM code revolution. Our source material is this really systematic, comprehensive survey on large language models built specifically for code intelligence. Okay, so let's unpack this. You've shared a pretty dense survey, and our mission today is very specific. We need to synthesize the 5 major turning points, the paradigm shifts, that really redefine this field, and then we need to pull out the most compelling predictions for the future of, well, autonomous programming. We want to give you a crystal clear picture of this monumental shift happening in software engineering. You know, moving from just simple code suggestions to full agentic autonomy.
Yeah, this survey is excellent for that because it provides a complete map. I mean, the entire model lifecycle. It starts right from the foundational data, the pre-training stuff, all the way up through the advanced decision-making agentic systems we're starting to see. And you can clearly see how the industry, well, it pretty quickly abandoned the whole idea of general-purpose LLMs trying to do code. The whole field moved toward these highly specialized tools, basically engineered to act like expert programmers.
And to follow that path, we have to start at the very bottom, the quiet, often overlooked revolution in the data that's used to build these code brains. So the very first turning point, it was some breakthrough in transformer architecture or anything like that. It was a realization about what the models were eating.
What they were being fed, exactly.
We shifted dramatically from training on, general internet text where code was just a tiny piece of the pie to these massive specialized code corpora.
And what's fascinating here is the sheer scale, but it's scale matched with this strict, rigorous governance. Early general data sets, something like the pile, it included a lot of code, sure, and it was about 825 gigabytes.
Which was huge at the time.
Huge, but it just pales in comparison to curated specialized collections like the Stack V2, which is dramatically larger.
Oh, right.
We're talking 32.1 terabytes.
That jump it's astronomical. I mean, that's 40 times the size. But as the survey points out, it's not just the volume, is it? It's the quality and the legal diligence behind that data that really defined this first key shift.
Precisely. Turning point 1 was the scale, but I'd say turning point 2 was the governance.
Yeah.
The precedent was really set by collections like the Stack V1 that made a very conscious decision to focus exclusively on permissively licensed GitHub repositories.
Ah, so that was to get ahead of the legal issue.
Exactly. It was a critical step to preempt the kind of legal concerns that just plague general data scrapes from the internet.
So it became a data engineering problem almost before it was an AI problem. How did they even ensure that level of quality and cleanliness at 32 terabytes?
They used these extremely sophisticated techniques, things like aggressive PII redaction to strip out any personal identifying information, and strict deduplication. Code is just inherently repetitive.
Oh, yeah. Boilerplate functions, common libraries, all that.
All of it. And removing that noise ensures the model learns real variety, real structure, instead of just memorizing the same snippets over and over. The industry moved from just hoarding raw data to building these transparent, reproducible, and legally sound data pipelines.
Okay, but let's pause there for a second. What was the tipping point that forced this hyper-specialization? Why did the general-purpose LLMs just hit a wall, even with bigger context windows?
Well, general LLMs are versatile for sure, but they just lack the depth and the robustness you need for professional software engineering. The survey points to 2 specific failures. First, they really struggle with things like domain constraints and security policies. And second, and this is crucial, They fail at maintaining what are called system invariants across large code bases.
Can you give us a quick example of a system invariant? Is that basically just making sure the model doesn't break things that are already working?
That's a great way to put it, exactly. An invariant is a property that has to hold true always throughout the execution of a program. So, for example, in a database system, a crucial invariant might be that a user can never have a negative balance. A general LLM might make a change in one file, but it often fails to check if that change violates an invariant that's defined like 200 files away.
And that leads to these really subtle, dangerous bugs.
The worst kind.
I see. And this failure, it relates directly to this concept of repository-level understanding.
Yes. Even if you could feed the model the entire repository in its context window, performance still degrades dramatically when the critical information like a specific API definition or that one dependency is buried deep in the middle of the context.
The lost in the middle problem.
That's the one. And that failure, really, it forced the entire field to pivot. They had to move toward LLMs that were explicitly optimized to navigate and reason over these huge interconnected code graphs, to act more like expert systems than just clever generalists.
Okay, so we've established specialized data, and that data creates specialized models. But once you have those, the next big hurdle, our third major turning point, was figuring out how to measure them properly. The standard for success had to evolve, moving from, simple correctness to your complex real-world engineering skills.
Initially, yeah, measuring success was simple. It was all function-level generation. We used execution-based metrics on suites like HuMedieval and MBPP.
Which are basically, here's a description, write the code.
Exactly. Code synthesis from doc strings. Did the function pass the unit tests? It was a simple yes or no.
And I'm guessing as the models got better, researchers realized those simple tests weren't tough enough.
Absolutely. The models started overfitting to the public test cases. They were just memorizing solutions. So to increase the rigor, they introduced strength invariants, HuMedieval Plus and MBPP plus play, and these included adversarially generated and hidden test cases. They were designed to catch models that were just pattern matching instead of genuinely understanding the problem.
But the real shift, the conceptual leap, was realizing that writing one isolated function, that's not what a software engineer does all day. The real challenge is system-level context, making changes that respect everything else.
That's where evaluation evolved into what we call repository-level understanding. Benchmarks like RepoBench and Crosscode Evil started assessing tasks that required navigating multiple files, understanding external dependencies, respecting the whole project structure. And critically, studies showed that models perform significantly worse on non-standalone functions.
The ones that have to read and integrate other code?
Exactly. Compared to the isolated problems they were used to, it was much, much harder.
So it's not just about generating code, it's about making the right change in the right place within a messy existing system.
Exactly. And then the scope of evaluation just kept expanding. It started to cover the entire software engineering lifecycle. We now have benchmarks for really sophisticated tasks like code editing, refactoring, even commit message generation.
The ability to summarize code changes in plain English, that's a complex skill.
It is. And this signaled a complete move away from just grading models on generating little snippets. We started measuring their comprehensive ability to support the full development workflow, from an idea all the way to deployment.
Okay, that covers the metrics. But if we know what good system-level code looks like, the next step is teaching the models how to actually produce it consistently. This brings us to our fourth turning point, upgrading the training pipeline beyond just, basic imitation learning.
The key shift here is from purely output-focused imitation, which is known as supervised fine-tuning, or SFT, to incorporating explicit reasoning-based methods. This includes things you've probably heard of, like chain of thought, where the model talks through its thinking. But also highly specialized methods, like program-aided language models, or PL.
Wait, let's back up on PL for a second. That's where the model generates code, but not for the final answer. It uses code to check its own logic as it goes, right? That sounds really computationally expensive. Why is generating more code in the middle actually better than just trying to get the final answer right the first time?
That is a great question, and it's the core insight of PL. It's a trade-off. You trade computational expense for reliability. For, say, a complex algorithm or a math proof, the model generates and executes little bits of code for intermediate steps. It'll run a calculation or check an edge case just to self-verify its logic before it commits to the final solution.
So it's using a deterministic calculator inside its non-deterministic brain.
That's a perfect analogy. And this transformation from just following instructions to thinking in code provides a dramatically more robust framework for complex programming. But the most significant step, I think, for achieving really reliable, high-quality code is reinforcement learning with verifiable rewards. RLVR. This is a massive turning point.
So why is RLVR so powerful for code compared to, I don't know, generating a novel?
It's because code correctness is fundamentally objective.
Right.
A novel's quality is subjective, but code, it either passes the test suite or it doesn't. There's no in between. RLVR uses that execution feedback, a unit test pass or fail, as a definitive non-negotiable reward signal. And that feedback loop lets the models refine their strategies toward verifiable correctness, which gives them a huge performance gain over SFT alone. It's the ultimate objective alignment.
That makes perfect sense. The code itself becomes the judge, jury, and executioner of quality. Now, speaking of training, the survey highlights something surprising about scale. We're always talking about massive token counts, but where are the practical bottlenecks in fine-tuning?
This is a fantastic sort of counterintuitive insight the survey uncovered. They found that when you're doing supervised code fine-tuning, or SFT, the global batch size is the dominant sensitivity factor.
Wait, really? Not the learning rate or decay schedules or something like that?
No. They showed that for high-performing models, like Qwen 330B A3B, accuracy degrades significantly if the global batch size gets bigger than, say, 256. It suggests that smaller effective batches preserve the gradient signal much better in the really complex structured distribution you find in code.
That is genuinely surprising. So if I'm hearing this right, when you're dealing with code which has these deep, precise dependencies and specialized syntax, averaging the learning signal across thousands of examples at once actually just smooths out the very features the model needs to learn.
Precisely. Larger batches, while they're faster, they average away that fine-grained gradient information that's crucial for understanding the nuances of, system invariance and complex dependencies. Smaller batches allow for more localized, structured learning that really respects the complexity of the code distribution. It reinforces this theme that quality and strategic process often beat just brute force scale.
That detail on batch size is crucial for anyone out there actually building these systems. But let's move to the culmination of all this, our final turning point, the application layer, which is the emergence of autonomous software engineering, or SWE, agents. These are the systems that move beyond just suggestion to active decision-making, planning, and executing multi-step tasks.
And we're seeing two distinct agent architectures emerge to tackle this full software development lifecycle. First, you have the single-agent iterative systems.
Like AlphaCodium, right, where one LLM just repeatedly reasons, reflects, reprompts itself, and uses automated tests for feedback.
Exactly. They're simple, they have low overhead, and they're surprisingly effective at complex tasks because of those reflection loops. But they do struggle with truly large, multi-component problems. And that's where the second architecture comes in. Multi-agent pipelines. These are systems like ChatDev and MetaGPT. They don't just use one LLM, they simulate an entire collaborative software team.
A whole team.
A whole team. The CEO, the CTO, the developer, the tester. They use structured roles and internal communication protocols to manage these complex multi-stage projects. They often mirror development models like waterfall or iterative. This division of labor enhances modularity and reliability for just massive undertakings.
This definitely sounds like the frontier. So, looking ahead, where are these trends taking us? What are the 4 key future trajectories the survey highlights that we should all be watching?
The future is really defined by addressing the current bottlenecks. First is multimodal integration. Agents are moving beyond just text. We need them to understand visual inputs, screenshots of a broken UI, a flowchart, maybe a UML diagram to generate code or analyze bugs. And benchmarks like Human Evil V are already measuring this ability to go from an image to a fix. Second is web-embodied intelligence. This means agents gaining competence in navigating the open web and complex external systems to perform long-horizon tasks.
Like fixing a bug that's documented on Stack Overflow, or configuring some complicated cloud service.
Exactly.
That sounds like basic web browsing to a human, but I'm guessing it's anything but easy for an LLM.
It is the current major bottleneck. The survey is very clear on this. While agents do well in closed, controlled environments, benchmarks for real-world tasks, like GIA and WebWalker QA, they show that even the top-performing models still achieve near-zero success on truly end-to-end open-world tasks.
Near zero.
Wow. The environment is just too unpredictable. It requires too many micro-decisions. The third area is standardized evaluation and feedback loops. We're moving toward what's called code-in-the-loop evaluation. This is where the environment automatically provides immediate feedback functional, even visual feedback, like programmatically rendering a front end, so the model can self-correct instantly, without a human. This is essential for robust autonomy. And fourth, security by design. As these agents get more access to production systems, trust is everything. The future requires integrating formal methods like model checking, which we see in projects like AutoSpec, and proactive defense like sophisticated fuzz testing, all to ensure verifiable correctness, not just a statistical likelihood of being right.
And we can't ignore the platform war that's heating up for the developers' attention. You've got the established IDE giants like GitHub Copilot, which the survey notes will default to a highly customized GPT 4.1 in 2025. Then you have AI-first systems like Cursor.
And countering them, you have these highly efficient terminal-based specialists popping up. Systems like Aider, which focus on fast human-AI collaboration using these really precise diff formats for code editing. And then there's Claude Code, which leverages Anthropic's new Model Context Protocol, or MCP, to manage external tools and planning all within a command line interface. The battle for who owns the developer workflow is clearly heating up, whether that's in a graphical environment or a text-based one.
That was a tremendous tour of the LLM code landscape. We've tracked 5 distinct turning points, from data scale and governance to rigorous evaluation, reasoning-based training, and finally, autonomous agents. The entire field has just fundamentally shifted from prioritizing raw scale to prioritizing data quality and verifiable performance.
Absolutely. The transition from, simple code suggestions to specialized reasoning-based autonomous agents. It represents a really profound move through deep, robust, and reliable code intelligence. The focus isn't just on what code the model produces anymore, it's on how it reasons about the problem, and maybe most importantly, how reliably it executes that solution.
So what does this all mean for you, the software professional, or even just the curious observer? The biggest lesson, I think, woven through all 5 of these turning points, is that performance gains are increasingly bottlenecked by quality, not just quantity.
We saw projects like Limo and S1, and they demonstrated that highly refined, quality-filtered datasets can achieve surprisingly strong reasoning capabilities, with remarkably few examples, sometimes as little as 800 to 1,000 carefully curated samples. And this raises a really important question for the entire field. In a world that's so dominated by multi-trillion token models, are we about to enter a new era where strategic data curation is definitively more valuable than sheer compute scale for achieving that final frontier of code intelligence? That's something to mull over as you watch the next generation of agents hit the market.